tá muito ruim, tá?
Tá muito ruim?
Tá. Quase não estamos te ouvindo. Pelo menos eu.
Melhor.
Tá melhor.
Aumentei o microfone aqui. Okay, they say my audio was really low. Yours is fine. Mine was really low.
Okay.
But you don't need to hear my beautiful voice, right? Just first. So,
Quase não estamos
again? Jesus Christ. Okay, we are live now. So let me introduce you guys, Professor Xiao Wang. Xia is a former student from UConn, where I graduated. We had some overlapping there for maybe 2 years, and we even shared the office. But let me go to the technical part. Xia is a professor in the Division of Statistics and Data Science at the University of Cincinnati. She has been working with many types of data, spatial data, high dimensional type of data, complex data, and so on. And she has many publications in the, best journals we have, and she's very active. And now she got interest, as she says, in variable selection, Bayesian variable selections, and she will talk to you today. It's an opportunity for you guys to, have a chance to get to know her. She will speak a little bit about the program she's participating. So, Xia, thank you for accepting our invitation. It's our pleasure to have you here. Very happy that you accept the invitation. You have maybe 15 minutes to give your talk, and then we open for some questions, okay?
Okay.
Thank you very much.
Yeah, thank you so much, Marcus, and thanks you so much for the invitation. I really appreciate the opportunity to do the presentation across the world, I think in both the spatial and the temporal science. Let me share my screen to make sure we should have done that earlier. See, can you see my screen now with the slides?
I'm muted. Yes, we can see.
Okay.
I think if you want to make it full screen, you should be
Yeah,
fine.
that's what I'm going to do next. Okay. So
Good.
yeah, I have a lot of buttons in front of me, so let me make sure those are out of the shot. So good afternoon, everyone. Today I'm going to talk about ongoing work, which I just started actually later last year, about variable selection for, well, it's mainly about variable selection for the generalized linear regression model, actually. But I think in the next 30 minutes, let me reset my timer. I'm going to talk about the application to the zero-inflated Poisson regression model. And the remaining time, I will see extension from the computational point of view, which is going to be applied to the logistical regression model specifically. Okay, this is a joint work with my PhD students, which I will talk about at the end of the at the end of my presentation. Okay, so the motivation for our work is this data set, which is record the doctor visits for patients during a certain amount of time. So the response variable that we are interested in is the doctor visit. And if we do the histogram plots, which this is the number of visits in the past 3 months in the survey, and then the bar shows the frequency of each of the counts. As you can see that apparently this data set has this so-called zero-inflated problem, and the standard counts distribution is going to be hard to accommodate in that. And now becomes the standard procedure. We all know that we can using the zero-inflated model to handle this zero-inflation problem, and that will lead to the regression model. We're going to have 2 equations, and variable selection will be on those 2 equations simultaneously. And the purpose is trying to using some predictor or covariates to explain the number of doctor visits for each of the patients. And age is one of the variables that were particular interest. It's been reported in the survey in a continuous scale. So there's options we can either include in age as a continuous variable, and there's some suspect if this is actually linear or nonlinear relationship when we including the age in our regression model. So one way is to including the polynomial kind of terms to accommodating this nonlinear relationship. Another way is to categorize the continuous variable into several groups. Like here, we can do 5 years per group and cut the whole range of the age between 25 to about around 65 to 8 groups, and the 25 is not showing here because that's a reference group. So we try both in our model. And besides the age, there's a couple other variables being collected in the survey. And I think that here's a total of 13, ranging from the health conditions to the kind of family or the income or employment status. Some of them are 1 or 0, and some of the continuous, like the education or income. Okay, so and then the common question we want to ask here is, with this many variables, and which one is actually important, and that will make a smaller model instead of a complex model for the future studies. So basically, this is what we're going to talk about in the coming 30 minutes. Is we're going to using a zero inflated regression model to handle the response variable and trying to find out of the collection of the variables of what are the subset of the variables are actually important in explain this explanation. And we're going to using the Bayesian methods, using the standard spec and the slab prior, which we will have a little bit more details, talk about this. And the algorithm is also pretty mature in this area to do the so-called stochastic search variable selection. And in the certain setup, the MCMC is going to be very fast. Okay? And this data actually has been studied in the previous study using the probability link when we talk about the zero inflation. But naturally, that logistic link is more commonly used in practice because it's easy to interpret with that odds ratio interpretation for the regression coefficients. And from our statistical point of view, not only in practice, logistic is kind of widely used, we also noticed that the link function is a structural component to consider when we construct our model. So the reason the previous study using the probit, because that probit, as we will see, will allow the Gibbs sampler setup. So the computation is more efficient. But the logistic, since it's a structural consideration, we should not sacrifice the computation kind of efficiency and for the correct specification of the model. So we still want to compare at least these two commonly used model for the data to see if there is a difference in the inference. And one of the focus in our study is trying to using the polygamma mixture representation of the logistic link selective function and make it has a closed form posterior distribution as in the probit link. Okay, so that's kind of the big picture, what we're going to talk about in the next few slides. And this is the setup of the model, the zero inflation for the counts data, and where we have the zero part. So this is the part where we call structure zero, when we have zero count, and that is actually is true zero in some of the ecological studies. See, when we talk about there's a fish count and maybe there's no fish, or maybe it's because the sampling error. So the counts of the fish out here, the count of the doctor visit is actually follows the count, the random counts distribution, but just by chance, it turns out to be zero. So this is the random zero. This is structure zero part. And this is how we the standard way to handle the zero inflation problem. And these are the two parameters, the probability of the random zero, which is Wi equal to 1, and which is going to be the parameter to be modeled in the zero inflation in the binary part. And this is another parameter, the mean parameter, which is belong to the standard counts distribution, and which we're going to model in our counts model parts. Okay, so the two parts of the zero inflation model, and the zero part and the counts part, both parts are using the linear regression structure, which we are familiar with. And just trying to compare with the previous study, for the counts part, we actually including a random effects, which is also a kind of standard practice here. And we assume this is individual effects. So maybe the individual has a different basic health conditions that will affect the number of the like random a factor not being accounted by the variable we included in the model, and we want using the random effects here to account for that. And we assume normal 0 with a sigma square distribution for these random effects. And other than that, the setup is pretty standard that we have this design matrix. We assume we have k predictor variables, and besides the intercept, we have the k vector of the regression coefficients. In our study, we assume the design matrix or the predictors are the same. Of course, it's straightforward to have different. It's possible to have different covariates here. So that's not going to be issues if you have different covariates. Okay, so now the question, as we said, that we want to have inference on the probability of the doctor visit and also the counts, the expectation of the number of the visit, see its relationship with the collection of the covariates. And the number of the covariates is going to be large, and we want to reduce the size of the model, and then we are facing, hey, which of the covariates we should be included in the final model. We want to make the inference. And that's a variable selection problem. And in Bayesian, we have the pretty straightforward way to help us to do that is to impose a spike and a slab prior. So usually what we do, we assume kind of routinely, we can just assume a normal 0 with a large variance, reasonable large variance priors on the regression coefficients, and we call that diffuse priors, and we run the model, have estimation, and see, hey, which one, the posterior credible interval, which one has a 0 in it or not, from the frequency point of view, to decide if a predictor is actually an important one or not. But that is going to be still, all the covariates is going to be included in the model. It's not doing the variable selection automatically. And using the spec and the slab prior, we still have that normal structure, but then we assume that if the variable is active, then it's going to be a normal 0 with a variance. Here we assume the variance is 1, so delta 1 means the value is equal to 1. If it's inactive, then the prior is going to be a normal 0 with a small variances, and we just plot the effect of the prior, how that affect the variance of the normal distribution here. So this is the prior on regression coefficients. So we're just using one of the regression coefficients as an example. The same structure is imposed on all the regression coefficients with mean 0 and this variance. And we put the priors, and this is the k components here. The tau k alpha is going to be sampled either from the V0 alpha. Here in our study, we fix it as a very small number. It's not necessarily always that case. You can, depends on your study. You can, some of the study, we're going to have this one related to the number of the parameters. But in any case, this variance is going to be much smaller than the variance here when the variable is active. And in our study, we assume that the variance is 1 when the variable is active. And that basically means the alpha k has a normal 0 kappa alpha distribution, and the kappa is the inverse gamma distribution. And if it's inactive, then we have this very small variances here. So this value is going to times the inverse gamma random variable. And here we can either have the V0 alpha equal to 10 to the negative 5 or 10 equal to negative 4 values. And we did need to do some tuning. Okay, this is something I feel kind of inconvenience when we're using the spec and the slab prior. We do need to do a lot of tuning of the hyperparameter values for data set to see the estimation and the convergence to check that to decide the final hyperparameter value we use in the study. But in any case, that this is, we're going to have this slab and the spike prior, and to tell us at the end of the study by the posterior probability of inclusion for each of the regression coefficients, if it's active or it's inactive. Okay, so that's how we do the variable selection. And as we said, that link function is something we want to consider. And it's easy to understand that from the point of view of latent variable, which is introduced, discussed in Albert and Chep 1993 paper with the response variable as 1 or 0. And we set up the regression model. And we basically, that paper assumed that the 1 or 0 is discretize the continuous process, which is beneath the 1 or 0. So we have the DI continuous process. And it's either, if it's greater than or equal to 0, then we observe 1. That means we have this random counts from the counts distribution. If di is less than 0, then we have that structure 0, which is wi equal to 0 or yi, and also yi equal to 0. And this di is assumed to follow this distribution. This is a part, actually the same structure as the binary regression model part, but we also impose a random variable here, the vi. And this random variable actually is the random variable decides the link function. So in the previous study, they assumed the vi is a normal 0-1 distribution, and that is leads to the so-called the link function we are familiar with, the probability link, and then everything becomes Gibbs sampler, so they can do the MCMC pretty efficiently. And they kind of see the challenging in logistic because we have the vi, which is logistic distribution, and then the likelihood function is going to be like this. So this is all standard, so we will talk about that later, but the key point here is this is the density function decided by the distribution of the vi. And if this is a normal density, then it can be combined with the prior we imposed on, which is either the diffuse prior or the spec and slab prior, and it's all normal. Then combine these two together, you can, sorry, not these two. Combine this one with the prior. I think I will show it here. Yeah. Combine this density, normal density with the prior, normal prior, then the posterior. I think if you have taken the Bayesian static classes, you know that the posterior for the alpha is going to be normal. We just need to work out the details of what is the mean and the variance for the normal, for the posterior alpha. Okay, so that is the advantage using the probability link. And using the logistic link, as we have seen here, logistic link has this, with the VI's logistic link, then what we have, the density function is going to have this format. So this is the density function for when we're using logistic link, and combined with the prior, when we're using the normal or the spec slab prior, what we found is that there's no closed form, no directly closed form we can see from this posterior distribution. And we have to using the Metropolis-Hessian algorithm or adaptive rejection algorithm. And that is particularly computationally expensive when we have a large number of the covariates. Okay, so that is what we're trying to avoid. We want to have the closed form, the nice Gibbs sampler, as we did for the probability link. So the way we're going to do that is we're trying to rewrite this likelihood function as a mixture of the so-called the polygamma distribution, which is introduced in 2013 by Paulson's paper on using the polygamma for logistic regression model. And this is that polygamma is actually the infinite summation of the scaled gamma distribution. So this is the density function, but that is not really of interest for us. And I think they have the software to take care of all the sampling. We can make use of that. And what is interesting and is important for us to understand how to rewrite that likelihood function under the logistic regression model to the closed form is these two properties. The first one is you can see that based on the polygamma distribution, and what we can do is for the function like this, which is similar to our logistic likelihood function, it can be written as the scaled mixture of the polygamma. Okay, so this is the normal scaled mixture with the polygamma distribution, and this is the one thing we're going to make use. You will see its application pretty soon. And another property is very important. Will help us to find the posterior distribution for the psi is this so-called exponential tethering of the polygamma distribution with the general parameter b and c as an exponential tethering of the polygamma with the b parameter and a 0. So this is the one we're going to revisit this one to see how it's applied to derive the closed form posterior distribution for the latent variable psi. Okay, so let's see how we apply these properties to overcome that challenging. So this is where we got stuck in order to have the closed form posterior when we're using logistic link. And based on the property, the first property for the polygamma distribution, this type of functional form can be rewrite. Oops, sorry. Yeah, here. Okay. So we're using this property just in matching the term. So basically what I did here, just matching every term, and that's how we got this term here. Okay, so we can rewrite this function as this, and then combined with the posterior expression, replace this part with this red part here, which I just derived by the property for the polygamma distribution. And when you look at it, what's happening here is we have distribution of alpha, which is actually integration of the joint distribution of the psi I, which is the polygamma distribution, and alpha. So you can imagine this is a proportional to the joint distribution of these two random variables, and we marginalize out the psi I, okay? And this implies that the joint posterior distribution of these two random variables. So we introduce the psi I into our model and look at the joint posterior distribution is of this format. So I just removed that integration part. So do not marginalize that. And now, well, the nice part is if we conditional on the psi I, then the posterior distribution for alpha now becomes, this is the prior, which is either the diffuse the prior or the speckled slab prior, which is normal. And if you look at it here, I think we are familiar with this format is the quadratic term involves alpha. And even without working on the details, we know this is going to be proportional to a normal distribution. Okay, so it's the multivariate normal. We rewrite it, combined with the prior, rewrite it, and this is the posterior distribution of the alpha is multivariate normal with the mean and the variances, and we can just sample from the multivariate normal distribution. So we have this closed form. Another thing is that, well, in order to do this, the price we paid is we introduce the psi, okay, polygamma distribution. And now we need to sample it from the posterior distribution, okay? If we look at it, the posterior distribution for the psi is, again, based on the joint distribution. We just remove this part, okay? Keep this part, that's the psi. And for each of the psi I, we're just including one of the exponential term. And here we're using the property 2, okay? It's proportional to this, and we're just adding a constant here, which is the integration for the numerator. So it's still proportional to this expression. And this is exactly where the property 2 for the polygamma distribution we can make use of. And we know if it satisfies this type of format, then it is actually the psi follows a polygamma distribution with these two parameters, B and C. Okay. With that, we can, the latent polygamma random variable also has a closed form posterior distribution, which is a polygamma with these given parameters. Okay, so with this, we kind of solve the challenging in the logistic regression model likelihood function. Do not give us the direct posterior closed form posterior distribution, and we can sample. And that's the methodology part. I think that's a key point how we overcome that challenging. And here's a discussion. I think we are particularly interested in see how the link function are going to affect the variable selection inference. So we did some simulation, as we all do these days we do a large scale simulation. So first we simulate the data from the logistic. So the true model is the zero inflated Poisson, but with the logistic. And we have the setup with either 24 or 48 covariates in our model. And out of those 24 or 48, 1/3 is no signal, so it's inactive axis. And 1/3 is weak signal with the beta equal to 0.2, and 1/3 is strong signal with the beta value is equal to 0.5. And the same setup in the zero regression part. So for these two part, we have the same covariates and the same regression coefficients with a strong, weak or no signal groups. And we also have the number of observation, either 1,000 or 2,500. Also for the covariates, we consider that there's all the covariates not correlated. All the 24, 48 covariates are correlated using the kind of the AR. I mean, the raw parameter, like depends on the distance between the covariates. So 0.8 is a strong correlation. We see how these factors are going to impact the variable selection. And we fit both the probability link and the logic link. So this is the posterior inclusion probability. The first number is the fitting result from the probability link, and the second number is the fitting result from the logic link. For the 8 combination of the scenario, we simulated 50 data points. So this number is actually the average across the 8 or 16 no signal regression coefficients and across 50 data set. So it's the average values. What we have seen here clearly, the choice of link function has basically no impact on the results in the counterpart of the model. And the impact is mainly on the zero part, which is natural, I think. And there's a systematic impact of the different choice of the link function. Is we can see that systematically, it doesn't matter under what situation, which of the 8 simulation situation we are discussing about, the posterior inclusion probability is lower in the probability link compared to the logistic link. Okay, it's always the case across different weakness, strengths of the signal of all the magnitude of the regression coefficients. Besides that, generally we see that the sample size increasing will improve the variable selection result, and the smaller number of the covariates will improve. And the impact of the correlation on the variable selection result is not really clear, which we'll see later. And that is where we want to do more simulation, see how this correlation across the variables have the impact on the variable selection result. But these are generally impact on all the model fittings. But specifically for the models, for the link functions, we see the probability has a lower rate to including the variables. Okay, and that can be explained theoretically. It should be the case because when we're using with the same data set, same variable included in the model, run the model, one with the logic, the other with the probability, we know that the estimation of the regression coefficients and the logic link has an approximate relationship between that and the probability link. And the magnitude approximately for the logic link is going to be greater than the constant times the alpha time, the regression coefficients estimated under the probability link. Okay, and this constant is actually greater than 1. And you can check that is approximately actually the regression coefficient and these 2 link functions approximately has the this numerical relationship. Okay, so and that gives us the idea that the logistic link model tends to give us a larger model compared to the probability link model. And we also, the second simulation, similarly, similar setup of the number of covariates, the strength of the signal, magnitude, the size, and the correlation among the axes. Now we are generating the data using the probability link. And similarly, we see the same pattern between these two models. But we also see sometimes their performance are similar under certain simulation scenario. And to visualize, so this is just a look at the posterior inclusion probability for each under each scenario. We want to see the overall performance of the variable selection. So we use the so-called the MCC. That will tell us overall how the model selection performance under each of the models. So similarly, we have the 8 scenario that in our simulation, and the first bar, and we do the box plot of the MCC values for the out of those 50 data set. The first bar chart, the box plot is for the logistic fit, and the second one is for the probability fit. And this is for the MCC result for the count part. And same as the table shows, there's not much difference in the count part. It doesn't matter if you're using the correct link function or not. And also it's clearly shown that the best performance is when we have a large sample size and no correlation among axes, and also the covariance number is relatively small. And when there's a correlation, generally we see they're reduced in the performance, but not really very clear how that is going to affect the variable selection. Again, but that's general across the link function models. So, and what is make a big difference is in the binary part. And this is when the data is logistic, and we fit the logit model and the probability model. So not surprising, we see the true model has overall a better performance compared to the I would say the wrong model, the probability model. So the overall MCC is higher under all the situations. But what's interesting is when we look at the data is generated from probability model. Okay, then we fit both probability and the logit. Their situation actually logistic has a little bit better performance compared to the probability. And well, the probability as a true model, it outperform the logistic when the correlation is larger, which we can see the difference, especially in here, the difference is much higher than what we have seen here. So again, the correlation structure is something we want to study further to see how that impacts the variable selection under different link function. But what we do observe here is, first of all, link function does matter. In the situation that we, at least we in practice, at least we should compare the different link functions. And also it's interesting to see that their situation, the wrong link function actually has a better performance in our simulation setup, especially when the sample size, the data size is small, and when the variable is larger. So it looks like logistic with a heavier tail perform better compared to the probability, which is the true model. Okay, in the sense of the overall variable selection across the different groups. So that's something motivate, and this is a motivation for us actually want to fit also logistic link to that German study data set. And we here just show you the results. We including the age as a continuous. We did try the one with the categorized age, and the model is much larger because there we also study the interaction effects between age and the health status. So what we noticed there, the model fitting does not improve. I would say it's not better than when we including the age as a continuous variable. So that's why I only reported results here. So we fit both the logit link and the probability link, and this is the counterpart. So not so similar in our simulation setup. We see they're pretty close estimation result under these two link functions. And this is the fitting with the diffuse or the regular normal with mean zero and the variance, large variance on the data set. There's no variable selection. So we can see that there's some consistency, but there's also some difference in the model fitting. Like this one is being selected if we're using the 0.5 posterior inclusion. But if you look at the HPD of the credible interval, we see that 0 is being included. So there's some difference when you do not do variable selection. And we also including the general, the MLE estimation, just for comparison purpose. And again, that like this one, the p-value, if we just look at the p-value is large, but using the variable selection, these are actually important variable being included. So this is the 0 part. And well, assuring that what we have seen here for this data set is the link function, both link function give similar result. Okay, even for the square term of the age, I would say the posterior inclusion probability is pretty close. So they're consistent, at least for this data set, it's okay to using either the probability or logit link. And we remember that we do variable selection. One purpose is we want to do the prediction for the future prediction based on the current model constructed. So we will also want to compare the model from the science of doing a prediction. So we use the cross validation, validated log scores. And the original version of this measurement is computational expensive because we need to fit the model without one observation and then do the prediction for that one observation out of all the n observations. So we use the simplified version, just randomize the data, randomly order the data and select the first N1 to fit the model, and using that to do the prediction for the remaining N-N-1 data set and do the calculation. We repeat this process 10 times and how average the cross-validation log score out this 10 repetition and report that. So compare these 6 models with the age either continuous or categorized, using the diffuse priors without variable selection or the variable selection under different link functions. the larger, the better. So what we have seen here, overall, the age categorized is not going to outperform when age is continuous. So we'll stick to the continuous, including the age as a continuous variable in our study. And the diffuse one definitely has a worse performance when we have the variable selection or kind of parsimonious model. And the link function, these two link function does not make a big difference, although it looks like the logic a little bit better, but I would not read too much into the after digits values. But this is consistent with our parameter estimation. So for this data set, it's okay to use in either probit or logic. But as I said, that one reason we want to try logistic is because in practice, logistic has that nice interpretation. So in a lot of area, people prefer to using logistic regression model. So it's good to have the tool to give to them. And actually, my students designed the R-Shiny app, which can apply this model automatically, and the practitioner only need to input, including the data set, and then they can run the model, have the model estimation result. So that would be interesting to see how that's being applied in practice. And just summarize what we discussed in the first part of my talk here, is that the application to the German healthcare data, and the key point is we want to have the variable selection for that two-parts model, and we want to have the flexibility in the link functions, and we introduce the polygamma latent variable there to make the posterior distribution of the logistic link become a Gibbs sampler kind of friendly, and we can do the comparison easily. Okay, so I don't know. I can, if you have a question, just let me know. I can answer either now or.
I think we can save it to the end if you want to present a little bit about your university and program and so on.
Oh, actually, I have a little bit more technical part before we go to the.
Let's keep everything to the end. I have questions myself, but I think we can keep it everything to
before
the
I introduce the beautiful University of Cincinnati, I still have some math equation to show. Okay, so one thing, what in our working on this project, what we noticed, we found that in practice is, recall that the posterior of the regression coefficients. So not on, especially for the logistic regression part. Okay, that's part we start our working on. The posterior is actually a multivariate normal. Okay, it involves the inverse of this k times k dimension matrix. Okay, so in our study of the healthcare data, that is about 13, 14, even with the categorized age is about 20, 30. Okay, so maybe it's still doable, but remember, keep in mind the computational order is cube to that number of the parameters, and overall, this overall complexity can, in order to calculate this, just this posterior distribution for the alpha. So we do have the computational challenge here, and in practice, it's not surprising we have a case larger. Okay, so this is another data set we worked on, is a gene expression data. The N is small, but the K is large. Okay, the original data actually has this many genes as the covariates, and the gender is something they also want to study, the gender of the mice, and they want to study the response variable is actually the one of the biomedical kind of measurement of the GPAD measurement. The lower level is good, it's going to reduce, kind of help with a disease caused by the obesity. And in the study, we categorize that continuous into either 1 or 0. So the 40 percentile is kind of like a cutoff point. If it's less than, and then it's we record W equal to 1 and 0 otherwise. And this is how the kind of the response variable and the gender distributed in our 16 mice here. And well, we didn't really working directly with the K equal to this large. In practice, people usually do a pre-screening. So we run the simple logistic regression model first and order the covariates, the genes based on, well, the gender always included. But the genes are going to run the simple logistic regression model, ordered based on the p-value for that regression coefficients. We only pick the top 99, and then from there, we run the logistic regression model and trying to see, still using the Speckens level prior. So still have these two variances, depends on if the variable is active or non-active. So this is ZJ is like the large and small variances indicator we had in the previous notation, so just a change of notation. But now we explicitly make it either 1, indicating the corresponding covariance included is active, or 0. Okay, so this is a setup, and what we did is we actually using the so-called skinny Gibbs sampler proposed by University et al. 2018. Where they divided the alpha, the regression coefficients into 2 parts, active parts and inactive parts, and correspondingly the design matrix, although being divided into 2 parts, the covariance corresponding to the active regression coefficients and one to the inactive inactive regression coefficients. Okay, so then look at this sigma alpha, which is the variance covariance matrix in the posterior distribution for alpha, which can be blockwise written. This is the original one. Okay, this is where the dimension is non-sparse, which is k times k dimension, and that's our challenging in the computation. And what they did, they do the approximation. So first of all, they assume the correlation between the covariance, the axis are 0. So basically this part disappeared. Okay, and then you have 2 blocks, and this blocks is a times a. Usually it's small. It's small even compared to the small sample size, but it's pretty small. And now we're still facing challenging here because this is the block, but it's k minus a, it's AC. Okay, it's still a large number. And they further assume that, okay, now, well, we standardize the axes and we assume they're unrelated to each other. We assume this one actually becomes identity, it's going to be identity matrix, and sorry, it's just the multiplication of these matrix together will going to set is equal to n. Okay, and then this will reduce the variance covariance matrix related to the inactive covariance becomes a diagonal matrix. So basically then this the computing is pretty easy and straightforward. So that then the main computing kind of cost is again on this small size variance covariance matrix for the active covariance here. So this is a key idea for this skinny Gibbs sampler. They do this, they sacrifice the correlation. When they estimate the alpha, they actually sacrifice the correlation and they do this approximation. Okay, and with that, as we have seen here, now everything's nice and sweet. So we sample the active regression coefficients from this posterior distribution. Now everything is of size much smaller than the k, and we sample the inactive one with mean they force it equal to 0 when it's inactive, and the variance they force it, as you have seen, they approximate as the diagonal matrix here. Okay, and then it's greatly reduced the computational complexity. This is the original one when we use exact Gibbs sampler, and this is a skinny Gibbs sampler. Okay, in the original paper, they also prove there's a theoretical result to prove the consistency of the selection of the model. So we'll skip discussion on that. And what we need to keep in mind is when we change a model, when we sacrifice something, I think this happened in our life too, that we do need to make it up somewhere. Okay, so this is what they do. If you sample everything, you sample the alpha from here, and you sample everything as they did in original posterior distribution, then you are actually not sampling from the correct posterior distribution. So we do need to do some adjustment. And the adjustment actually happened in the skinny Gibbs sampler is the sample, the ZI indicator. The ZI indicator is actually 0, 1. So the posterior is again the Bernoulli with the probability it's equal to 1 being active, which is expressed in this term. And the DJ is actually the odds between the ZJ equal to 1 or 0. Okay. And the blue part is the posterior distribution before the skinny Gibbs sampler approximation. And when we have that, in order to make sure we are sampling from the joint posterior distribution, the true joint posterior distribution, we do the adjustment when we calculate the DJ. So this is the whole thing together is the posterior probability. I mean, the term used in the posterior probability for the ZJ is equal to 1. Okay. And with that adjustment, now I think the algorithm showed that this is correct to the posterior and everything should be consistent with this setup. And we fit the model, we fit the logistic regression model with that skinny sampler, do the model comparison. So we fit 6 variable selection methods, and these 3 are non-Bayesian methods, and these 3 are the Bayesian methods. For the Bayesian method, that this is the green one is our model. And what we have shown here, this one has the lowest predictive error for the 10-fold cross-validation. So we divide the data into 10 parts and do the prediction with the 9 parts, we do it 10 times. I mean, each part we do it the same way, and we calculate the prediction errors, and the proposed method has the lowest one. I'll be honest with you, and this is not always the case. Okay, so the result is not very stable, but on average, our model is generally is lower compared to most of the other models. And what I want, this is actually the interesting to see, this is the exact gap sampler, so that's without a skinny gap sampling. And what we see here is interesting. At the end, the predictive error become larger. Okay, so this is we need to look further into the computation to see what make it the sample size. So basically, the x-axis is the sample size. So how many covariates you're going to include it. The posterior probability actually only suggests, if you use 0.5, only suggests using 1 or 2 genes as a predictor. But we kind of, in order to do the model selection, model comparison, we increasing the model size, and that is where the uncertainty comes from. We don't know if we including more of the variable has a lower posterior inclusion probability is actually making the model performance is worse or not. Just trying to understand what's going on, why it make it larger. But what we notice is our model kind of stable in the predictive error, and also this one, the right one, is the one in original 2019 paper where the skinny gap sampler is being proposed. And we can see it's also kind of stable. So using the skinny gap sampler actually kind of stabilize the predictive error somehow. Okay, but in their original paper, they didn't use in the polygamma representation. So they actually using the T approximation. So maybe that's another reason that there's some difference in the predictive error because they have additional approximation of the link function. But these are the 3 Bayesian methods, and these 3 are the adaptive lasso, MCP, and SCADE methods. And I think overall they always have a higher predictive error compared to the Bayesian methods. Okay, so I think this is all. Let me see. All I want to talk about technically. And I just want to thank my PhD students. So these are the 2 students working on the project. Haichao Zhang is in her 5th year, and she's going to graduate this fall. And she's the one, she has been working on the zero infinity Poisson model, and the variable selection is one of her project. And Eric just started on his research, and he just finished this semester, the skinny gap sampler project, and we're still trying to look in more details. There's a lot of question mark on we want to look further too, but they are doing a wonderful job to help me to make today's presentation possible. And with that said, also I want to talk further about as Dr. Price kind of remind me that advertise our program. I really want to do that actually. So in our graduate program, we have both PhD and master in statistics. And PhD actually is a program being existing for a very long time and being very successful. But we just changed it as PhD in statistics in 2018. Thanks for the the growth of the statistical field. Actually, the whole field is growing and become more and more attractive. Before we called PhD in mathematics with concentration in statistics, but now from 2018, our graduate students. PhD students have in their diploma, there's a PhD in statistics. And we have faculty, almost all our faculty actually is working in the area of Bayesian statistics and in different field and very active. As you can see the research, and we have a couple of faculty very good in the spatial and temporal and also machine learning and in the uncertainty quantification. And as I told Marcos at the beginning that the first time I came to Cincinnati, I'm very impressed by how the students, our PhD students, are supported during the program. It's different from a lot of STAT program. We have fewer students working as a teaching assistant. It does not mean that we do not want them to, just like there are high demand on our students from local company as well as the Cincinnati Children's Hospital. Almost all our students, upon enrollment recently, even just started a fresh PhD, they got an internship, either working at the Purple Gumbo's research lab, or the Cincinnati Children's Hospital, the Biostat department, or some local pharmaceutical company as an intern or as a research assistant there. Many of our students have publication in their after 2 or 3 years or working there, they have a couple of publication after graduation. Several of our students actually find a good position, academic position. They've been tenure track assistant professor in several universities, and many of us other students go to either government or the industry area. And the students are from all over the world, and I think they have sometimes I'm jealous because you can see that in the lunch, that the lunchtime, the whole group they're very happy to talk to each other, and so I think the Cincinnati definitely is a good place to consider if you're considering to pursue your graduate study and want to come to US. And definitely look at our program. And there's more information you can find on the website. And I was, nowadays everything's a barcode, right? I was surprised to see they actually have a barcode on our website. You can just scan it, you got more information. And application deadline is February the 1st. And definitely, if you have questions, you can, of course, contact me for that. So this is, if you want more details about what I presented, the contents, and we have finished a manuscript, and there's ongoing work, but I think we are preparing the manuscript, all the technical part for this project that's been done. And also, as I said, Hai Chao, she prepared a Shiny app. She's refining, but is going to release the public version. It's very easy to use. She showed me, I think it's really amazing, user-friendly. Okay, so that's all I want to talk about. And thank you so much for your attention.
Thank you, Shia, for the presentation. I don't know if the students have any questions. While they think, let me ask you a few questions. I have a few. So at the beginning, when you presented the zero inflated Poisson model, you included an IID term, the Poisson regression. Why you did that?
Yeah, that is the main reason we did that is to compare with the original paper, analyze the same data, but they use the probability link. And I think we understand why they are doing it. Because they say we're going to take care of the individual random effects. Maybe that there are some, let me see if I block. We included covariance, and though there may be some impact has not been explained for each individual, and we want to take care with this random error here. And I think another reason from a technical part of view is the author want to say, hey, we actually can do the Gibbs sampler for the beta, because if you assume this is normal, and what happened here, they conditional on the eta I, which is the log of lambda I, that you have the normal random effects. Okay, the eta I is normal because you're set up of that sigma I, and then you put we using the Speckner slab prior on it, and then the posterior for the beta for the counterpart is automatically becomes the Gibbs sampler multivariate normal. But I do not quite like it. I would be honest, the only reason I use that is because the original paper using it, we want to compare with the original paper directly. Because even if the beta is Gibbs sampler, when you sample the eta I, it's not. You have to using the metropolis testing because it's not closed form. But I also understand why they're also using it when you have individuals and you want to take care of that random effects. Yeah.
Yeah, probably they have over dispersion as well, right? Not only zero inflation.
Yeah.
Well, the second question is, you presented the simulation, and then you have no signal, weak signal, strong signal, right? And to say that, I assume all your covariates are, say, standard normal. They are all comparable, right? The axes themselves, they're in the same scale.
Yeah. Yeah, we generated all the x's as normal 0, 1. Yeah, that's
Okay.
that's what we should mention.
And you entered for me in a dangerous world where you compare the Bayesian with the frequentist. While in slide 18, you're comparing the selection methods you suggest or you present. By the way, this polyurn idea is very nice because that's always a criticism people say about logit. Oh, it's not conjugated, there's nothing you can do, let's use probit, right?
Yeah.
So this is very interesting. But so in slide 18, when you compare against the maximum likelihood.
Yeah.
Should you compare as well with the lasso regression to see if they select the same variables as the Bayesian models, or it's useless? Because the diffuse prior will be somehow related to the ML. But the SS probit or the SS logit, I assume will be more like a lasso kind of regression, right?
Yeah, you're right. You're right.
And then maybe check if they select the same variables might be interesting, not only because you see that, for example, this one you showed at some point that was not included in the diffuse prior, but was included in the selection. The point estimate changed quite a bit. And maybe that will happen to the lasso as well. I don't know.
Yeah,
it's just a suggestion. I've been probably published, so who cares?
Yeah, I think that's a good point. That's a fair comparison, right? We'll see.
My final question is: you compare the models through the prediction capacity, but you are studying a model selection paradigm, right? I was wondering. My question would be better than checking if the prediction is right at this point. Does this method select the correct covariates? Can we affirm that? Because that's what they do, right? It's a variable selection, and I want to show, okay, this method, we can really tackle the true variables, and that's why it has better prediction, because it's kind of getting closer to the true model, whatever that is.
Yeah, that's a very good point. We cannot do it in the real data, but we actually did that in the simulation data. We have that confusion matrix, which is not included here, to see that how the variable are doing in selecting the correct covariates. And that's interesting to see that, but it's kind of consistent that logics tend to more likely to select the variable compared to the probit. And let me see if I can.
If that's one conclusion, that's another thing. If that's one conclusion you get, that logit is better than selecting than the probit, maybe because of the tails. If you put a probit with, not a probit, a normal link with mean zero and variance pi square over 3, it behaves pretty much as a logit. In terms of behavior, it becomes very close. If you plot the cumulative distribution, basically you cannot see you can see, but the distributions themselves are very close to each other. Since it's a link and you can fix 0, 1, or you can fix 0 pi square over 3, I assume you will get the same power as the logit, but on the other hand, again, it's still misinterpretation, right? And now you find a nice way to do it in closed form. So I stick with the logistic now. But at sometimes people say, oh, I want logist, but the problem is it's not, conjugate. I'll just suggest use a normal 0 pi square over 3. You'll have very similar behavior to the logit, actually. And it usually works.
I think that's maybe even we can approximate the interpretation. When we use
probably approximate interpretation.
That's a very good point. Yeah.
If you go in the 50s book, probably there's some Taylor expansion that you can show that it would be close enough and into that. But anyways, let's see if any students have questions. Thank you for your presentation. Very interesting, this. Anyone wants to ask anything at all?
I saw the chat. I don't know if the question.
The chat. So this is a attendance chat. So they just write.
I already sent that.
Tons of message. Usually I can check, but it's just a attendance from the students. Well, I think we are on time anyway. So yeah, a little bit ahead of time. So if we don't have any questions, let me think